Welcome everyone to session 8C. This is broadly speaking, is going to include 4 talks on 4 very interesting works in economics and computation. I found it interesting that another thread that was connecting the 4 works we're going to see today are about challenges that come from information, both in terms of eliciting information or lack of information that we have to deal with. So I thought that's really cool to see. And we're going to see that playing a role in both options and scheduling, the first 2 talks, and especially the role of truthfulness. And in the second 2 talks, we're going to see this with looking at what are the challenges that we have to face in matchings when we don't know enough about the problem ahead of the time. So just a few words about how the session is going to go. We'll have 4 talks, and each of the talks are about 5 minutes of talk and 5 minutes of questions. During the talk, feel free to use the Q&A feature to type your questions, or wait until the talk is done to raise your hands if you want to ask any questions that you have live. And we won't stop the talks, but once the talk is done, we'll attend to your questions. Okay, so without further ado, we'll start with the first work, by Anna-Maria Kovich. Anna-Maria, whenever you're ready, you can, sorry, by Raghuvansh Saxena. Raghuvansh, whenever you're ready, you can share your screen.
Yes. Thank you. This is a talk on combinatorial auctions, and I'll start by defining the setting. We will only be concerned with 2-bidder combinatorial auctions where there are 2 bidders, Alice and Bob, that are participating in an auction where some items are for sale. These bidders enter the auction with a valuation function. So Alice has V1, Bob has V2. They're defined on all subsets of items. And the output of this function for a subset of items is the value that the bidder gains when they're allocated that subset. For example, if Alice is allocated the set S1, then she will gain value V1 S1. Similarly, if Bob is allocated the set S2, then he will gain value V2 of S2. The goal of the auctioneer is to find a partition of the items, for example, S1 for Alice and S2 for Bob, such that the sum of the 2 values, also known as the welfare, is maximized. And he wants to accomplish this goal using as few bits of communication as possible. This is the goal of the auctioneer. What is the goal of the bidders? It turns out that combinatorial auctions can be studied in 2 different regimes, each one with a different goal of the bidders. In the first regime, called a non-truthful auction, the bidders have the same goal as the auctioneer, and all the 3 parties in the system will work together to maximize the welfare. The other regime is the regime of truthful auctions, where the bidder's goal is to maximize their own utility, which may be different from the welfare. And in the truthful regime, because the goal of the bidders is different from the goal of the auctioneer actually needs to work harder and charge the bidders appropriate prices so that they help him maximize welfare. In particular, this means that a truthful auction in any setting will require at least as much communication as a non-truthful auction to get the same welfare guarantee. And the main problem that we study in this paper is whether this inequality is strict. We want to know whether there are settings of combinatorial auctions where, for the same welfare guarantee, truthful auctions need strictly more communication than non-truthful ones. In fact, we shall study a flipped version of this question. Instead of asking how much communication is needed to obtain a certain guarantee, we shall say, suppose a truthful auction and a non-truthful auction have the same polynomial communication. Is it the case that there are settings where truthful auctions have strictly weaker guarantees with polynomial communication than non-truthful ones? Okay. This central question has been studied since a long time, but is still wide open. On the one hand, there are settings where the guarantees known by polynomial communication non-truthful auctions match those known for polynomial communication truthful auctions. And on the other hand, there are settings such as XOS that I won't formally define, where we know that the best known guarantee for a non-truthful polynomial communication auction is 3/4. The best known guarantee for a truthful polynomial communication auction is 1/2. But because there are no upper bounds better than 3/4, there is no separation between truthful polynomial communication and non-truthful polynomial communication options. Our main result is exactly this upper bound. We show that if the valuation functions are from the class XOS, then any truthful option with a polynomial communication cannot get approximation, which is 3/4 of the optimal. In particular, this means that there is a separation between the power of polynomial communication, truthful and non-truthful option. And I would emphasize that this is the first separation. We work with 2 bidders and XOS valuations, but you could work with any number of bidders, 3, 4, n bidders, or you could work with any valuation class such as submodular, subadditive, additive, any class that you can think of. This is still the first separation between the corresponding truthful efficient option and the corresponding non-truthful efficient option. Okay, this was the result, and I will now finish off with one line on our techniques. The way we get this result is we take 2 copies of the combinatorial option and run them in parallel. One copy is a high copy with a high welfare. The other copy is a low copy with a low welfare. In particular, low is less than 3/4 of high. And because low is less than 3/4 of high, the auctioneer must give an allocation from the high copy. This means, in particular, that the auctioneer must find out which one is the high copy. But then we're able to show that in polynomial communication, the auctioneer cannot tell the high copy from the low copy. Therefore, he cannot tell which is the high copy, and therefore he cannot get a welfare better than 3/4. And this concludes the proof. Thank you.
Thank you. I'm going to unmute and clap. You can do that on your homes too. Thank you, Raghuvansh, for a great talk. If there are any questions, you can either raise your hand or use the Q&A to type your questions. We'll give it a few seconds. So question, Tim Roughgarden is asking, could you say more about what you mean by ideas from BMW 18?
Okay, so in more detail, BMW 18 show that if instead of outputting an allocation that has high welfare, you only want to estimate what the welfare is, then, and this corresponds exactly to determining if the welfare is high or low, then you cannot do it in polynomial communication. However, BMW also say that this does not imply anything about actually the auction, which requires us to compute a good allocation. And what we do is we extend BMW from the decision problem, where they only need to determine or approximate the welfare, to the actual auction, where you need to output an allocation that has good welfare.
While we're waiting for more questions, let me just ask a follow-up clarification. So is this fair to say that then the lower bound that was in the BMW 18 was for decision version, where you don't know basically if it's high or low, but you can still guarantee that you can get a good, there's an allocation that gets good welfare. And in your setting, you're trying to use those ideas by having 2 copies to show that even the allocation problem itself is difficult. Is that fair to say?
That is fair to say, but I would also like to say something that makes it more interesting. The BMW instance, usually in complexity theory, the decision problem is weaker than the allocation problem. So generally, a lower bound for the decision problem would imply a lower bound for the allocation problem. But in this setting, we know that the BMW 18 instance that has a lower bound for the decision problem is actually admits a good allocation mechanism. So a lower bound is not possible for an allocation, for the allocation problem. Our instance, which has a lower bound for the allocation problem, admits a good decision mechanism. And therefore the BMW lower bound will not work for our instance. So in this happens to be one setting where the decision and the allocation problems are incomparable, which is another interesting fact, I think.
Thank you. Let's see, are there any other questions? So we have about a minute left of this. Let me ask you, what are the is there any general interesting open problem left that you think your work can maybe shed some light on, or it would be what you would look at next?
It's not what we're looking at next, but one very interesting problem is that we do show that this upper bound is strictly better than 3/4. But still, we only improve it by a very small constant, which is sufficient for this separation, but it is not sufficient to like pin down exactly what welfare guarantees truthful auctions can provide. Specifically, the best known truthful polycommunication auction, which is actually trivial, just give the items to one random bidder or run VCG on the grand bundle, gives an approximation of 1/2, and no auction is known with an approximation guarantee strictly better. So if you can get an auction that has approximation strictly better or get a lower bound of 1/2, they're both very interesting directions.
Cool, thank you. Last chance for any remaining questions. Okay, let's thank Raghuvansh again. Okay, you can unmute if you want or do this at your home. Thank you so much. Raghuvansh, you can stop sharing screen and we can switch to the second talk now. Our second talk is on the Nissan-Ronen conjecture for submodular valuations. And Anna Maria Kovich will be giving this talk.
Yes, thank you. So let me introduce the problem. I'm afraid I won't tell about the techniques now. If you are interested, you should watch the video. I just try to introduce the problem and the result. So this is the unrelated machine scheduling problem where we are given n machines and m tasks, and the running times of every particular task on the different machines are arbitrary non-negative values, not related to each other. And we want to, or we have to schedule the task, so give each task to exactly one of the machines so that the make span, the maximum completion time, is minimized. There exist two approximation efficient algorithms for this problem, but here in the sense of polynomial time algorithms, but here we are not interested in polynomial time algorithms. Actually, we absolutely don't care about the running time of our algorithm. We would like to have scheduling algorithms which are truthful, or more precisely, weakly monotone algorithms, because these are the ones which can be complemented by truthful payments, so that even if the running times of the machines are private values known only to the machines themselves or some agent possessing the machine, then these payments motivate them to report the running times truthfully. And then the weakly monotone algorithm, together with this corresponding truthful payment, is called the truthful mechanism. So this is kind of a mirrored combinatorial auction, in the sense that the bidders here don't have valuations for the items but costs, and they don't pay for the items but get paid for performing the tasks. A simple example for a weakly monotone allocation is the allocation of the VCG mechanism, which simply gives each task to the fastest, also independently every task to the fastest machine for that task. VCG is a generalization of the second price auction, and it minimizes the sum of the costs of the agents, but it has a very bad approximation of the make span, which is not the sum of the costs, but the maximum cost. So the approximation factor is n, the number of the machines. Here you can see on the example why this is the case. So here in this case, each task is given to the first machine and it produces a very, very high make span. Nizan and Ronan, 20 years ago, had a famous paper in which scheduling mechanisms were introduced. Actually, algorithmic mechanism design was introduced in this paper, and they formulated the conjecture in this paper already that actually no better approximation factor is achievable by any weakly monotone allocation algorithm. So actually VCG is an optimal truthful mechanism in terms of approximation ratio. So here is the current state of this problem. Despite the conjectured lower bound of n for the approximability by truthful mechanisms, the known lower bound is a small constant. The current best constant is 2.755, is actually a very, very fresh result. And the lower bound of n has been shown only for certain restricted classes of mechanisms, among which this class of anonymous mechanisms. So this paper is the deepest result. And here comes our result. So the original conjecture concerns additive cost functions, so meaning that we add up the running times of the tasks on the machine to obtain the cost of the machine, and we show in the paper a lower bound of about square root of n in case that only one of the machines is allowed to have a slightly broader space of valuations or cost functions than the additive space. It actually doesn't really matter what this broader space is. The main thing is that this is higher dimensional than the additive space, but it can be an arbitrarily narrow extension of this space. So it can be submodular, supermodular, or epsilon additive, meaning some almost additive class of valuations by any reasonable definition of almost additive. Yeah, so that's the result, and thank you for your attention, and ask your questions.
Thank you. It's time for questions, so let's see if there are any already. So while we wait for questions, I know you didn't have time to, of course, talk about the technical details, but I was wondering, for those who watch a longer version of the video, if there's anything you want to say about, you know, why this higher dimension, like what is it with this higher dimensional or submodularity that is helping us prove this result, and whether or not we can take some of that to the additive world as well.
I didn't understand your last sentence.
Yeah, so is there, I guess, what can we do for the additive world with additive valuations only? Is there something that we can get with your techniques, or can we learn something from these techniques?
We don't know. Yeah, so the point is that admitting more than additive valuations for one of the players kills some sort of mechanisms, the task independent mechanisms, and these mechanisms are making us trouble because they behave in some non-linear way. But we have technical results or certain, yeah, so technical tools which we hope that we don't know if we can use these technical tools also for the additive case. Somehow, if we learn how to deal with the with these kind of task independent mechanisms. So actually we restricted. We know much about the mechanisms whom we don't like, and they must be task independent. And if we can somehow show something like that, this is not true, but something like that dependence is something like an equivalence relation, then we could partition the tasks somehow, and we would have classes of so independent classes. It is not an equivalence relation, otherwise we would be ready.
Yeah,
but if we can do something like that, then on the other hand, we would have dependence. If it is completely dependent, then we have the lower bound again. So yeah, we don't know, we keep working.
Let me ask one of the questions from the audience. Tim Roughgarden is asking, any hope for a lower bound against randomized mechanisms?
I don't know. I don't. I'm not dealing with randomized mechanisms.
Okay.
I don't know. Maybe Yorgos is probably here.
If an audience wants to be unmuted, they can raise their hand. Okay, you have maybe 30 seconds, so go ahead.
Hi. So yeah, regarding lower bounds for randomized mechanisms, I think that maybe some of the ideas that we had, I think that they could be used for randomized mechanisms, but we haven't really tried this. But I think that I believe that some of the ideas, yes, could be used, especially for universally truthful mechanisms, for showing lower bounds for this.
Okay, so this is probably a good thing to chat over in the break. Let's thank the speakers again. And we are going to move to the third talk. Anna-Marie, if you can stop sharing your screen.
I can't stop sharing, but you can stop me sharing.
Mary, can you help Anna-Marie a bit with that?
Yeah.
Thanks. Okay. So our third talk is titled Towards a Better Understanding of Randomized Greedy Matching. And Yuhao Zhang is here to talk about that for us.
Okay, I'm unmuted. Okay, I'm unmuted now. Can you hear me? And can you see the poster? Yeah, okay. I'm Yuhao Zhang, and I will give a very brief introduction of our paper towards a better understanding of randomized greedy matching. First of all, the models we study is the oblivious matching problem and its weighted generalization. In the problem, we are given an oblivious graph with unknown edges, and what we need to do is to decide the probing order of all vertex pairs. And at the time we probe a vertex pair, we will know. We will actually know whether or not there's an edge between them, and if there's an edge, and if the two endpoints are not matched before, we must match them at this time. So the goal is to maximize the matching size we finally get. In the weighted version, we actually have a weight function WV for each vertex pair, and this information is not oblivious. And the goal changed from maximize the size to be maximize the weighted sum of the matching we finally get. Okay, we observed that many well-studied algorithms can all be viewed as a family of algorithms called vertex iterative algorithms. It means we will decide the probing order by a specific decision order and each vertex preference order. That means we will let vertex make decision following the decision order, and at vertex decision time, we will probe vertex pairs following that vertex preference order. Okay, and a very good example is the modified randomized greedy matching algorithm MRG. To view it as a vertex iterative algorithm, it's just uniformly random decision order and then uniformly random preference order for each vertex independently. And our algorithm is called random decision order, RDO. It's actually just a weaker version of MRG. The same as MRG, it's uniformly random decision order, but then it even allows arbitrary selecting of preference order for each vertex. Okay, in the weighted version, our algorithm is called perturb greedy, and it's a weighted generalization of RDO, the randomized decision order algorithm. And at first, we need to fix non-decreasing function G and then uniformly random rank YV for each vertex V. Finally, we just probe vertex pairs in descending order of their perturbed weight, which is 1 minus G min YU YV multiply the weight of the pair. Okay, so what's our result? We prove RDO is 0.639 approximate in unweighted bipartite graph and 0.531 approximate in unweighted general graph. For the weighted case, we prove perturb gradient is 0.501 approximate in general case. The contribution is, at first, we improved analysis of MRG. By the result of RDO, as I said before, it's just a weaker version, so we can the RDO's ratio can directly apply the ratio of MRG, and 0.531 beats the previous best ratio of MRG. And we also improved the best ratio of unweighted oblivious graph. Previously, it's 0.526 by ranking algorithm. And the 0.501 approximate ratio is the first non-trivial result for weighted oblivious matching problem. And a little bit about the technique. Basically, we use a framework called gain sharing framework, and to handle the bipartite case, we just need to apply a very classic property called alternating path property. But in general case, we raise we need to raise some new ideas. We use crucial idea called victim and compensation, and that's let us get some extra gain when the alternating path property does not hold. And in the weighted case, I can't say many things, but basically it's just a weighted generalization of gain sharing rule and weighted generalization of compensation rule. Okay, and a very one interesting discussion. As I said before, we found out many algorithms can be viewed as vertex iterative algorithms like RDO, IRP, MRG ranking, and F ranking something. They use different randomness on decision order and preference order independently or correlatively. I'm very interested in their relationship. Okay, that's all. Questions?
Thank you, Hao. If there are any questions, please either raise your hands or post on the Q&A. We have a question by Shang Shang, and they're asking, is any of these results tight?
No, it's not tight. And interesting, the upper bound, the negative result is the case. The negative result is all made by unweighted bipartite graph. So we even do not know general graph is general graph worse than bipartite graph, and is weighted case worse than unweighted case. The ratio is about 0.79 something, 79 something. I can check it for you, maybe.
Okay. Let me ask another question by audience. Sefer Asadi is asking about the model. Currently in the oblivious matching, you pick an ordering of edges and then run greedy algorithm. Is there any work on changing the greedy algorithm with some other online algorithm, similar to random arrival online matching problem, for instance?
Random Yeah, the random arrival algorithm is just the same as we make a uniformly random decision order. Is that okay?
Sefer, do you want to, yeah, let me unmute you. Go ahead.
Okay, can you hear me?
Yeah.
Yeah.
Okay, so first, nice result and very nice talk. Okay, so let me ask you these things. Currently in the oblivious matching, when you fix the ordering, the algorithm becomes fixed, no? You just pick
Yes.
if it exists, okay? Now, suppose I allow you to change your algorithm slightly also. For instance, even if you see an edge, you may not decide to pick it now, but this is an online algorithm now. If you didn't pick it, you cannot come back and pick it later. Does this make sense?
Yes, but what you talk about is another setting, the online setting.
Okay, so are there some studies there that people try to find the best ordering? So it will become something like best order online matching, probably. Do you know, is there any work there?
Yeah, actually in online setting, we may not have we cannot change decision order, right? The decision order is given by the adversary. It can be random arrival or adversary arrival, right?
Yes.
So the thing is the preference order. So in online matching problem, people may you may think about the ranking algorithm I propose. Do you know the ranking algorithm?
Yes, yes.
Yeah. So in the online setting, because we cannot change the decision order, so the only thing I know is to make the ranking algorithm to use the correlation of the ranking algorithm to beat the 0.5 barrier.
Okay, perfect. Thank you.
Yeah.
Okay, thank you for the talk and thank you for the question. That's the amount of time we have for the questions. Let's thank the speaker once again. Okay, so let me. Okay, so the last talk is called Stochastic Matching with Few Queries, 1 minus epsilon approximation, and Sohail Behnajad is here to talk about it.
Thanks, Nico, and hi, everyone. My talk is on the stochastic matching problem, and it's a joint work with Mahsa Darakhshan and Mohammad Haji Aghay. So let me get straight to the problem definition. We are given an arbitrary graph G along with a parameter P, and then each edge of G is realized independently with probability P. So basically a realization of G is a random subgraph that includes each edge independently with probability P. We are unaware of this realization, but what we can do is to non-adaptively query a subset of edges of G to see which are realized. And then the goal is to find a large realized matching by querying few edges per vertex. Okay, so in other words, and slightly more formally, the goal of the problem is to pick a degree-bounded subgraph Q of G that achieves a large approximation factor defined as the following ratio. It is the expected size of the maximum realized matching of the subgraph Q that we picked over the expected maximum realized matching of this whole graph G. Problem has natural applications in kidney exchange, online labor markets, online dating, and also on matching the sparsifiers. So let me overview quickly some of the related work. In 2015, Blum et al. Introduced the problem and showed that the half approximation can be achieved by querying O of 1 edges per vertex whenever epsilon and P are constant. The approximation factor improved over time, and then the state of the art is a 2/3 approximation of Assadi and Bernstein. A few remarks about this last result. The 2/3 approximation of Assadi and Bernstein is tight for the algorithm that they use. But more importantly, 2/3 is in general a natural barrier for the problem, in the sense that if we add just a little bit of correlation in edge realizations, then it could be proved that any better than 2/3 approximate subgraph has to be very dense. So in other words, the problem does not admit better than 2/3 approximation unless we pick a dense graph in this extended model with correlations. In fact, all the prior works also extend to this model with correlated realizations. And that kind of explains why all of them were stuck behind two-third approximation. So what we do in this work is to show that not only one can be two-third approximation in the stochastic matching model, but in fact, a 1 minus epsilon approximation can be achieved. So in other words, what we proved is that for every positive epsilon and any realization probability P, any graph G has a subgraph Q of maximum degree dependent only on epsilon and P, such that the expected maximum realized matching of Q is at least 1 minus epsilon times the expected size of the maximum realized matching of G. Okay. So in fact, it can be shown that dependence on both epsilon and P is required to achieve a 1 minus epsilon approximation. So in terms of the parameters that this degree depends on, our algorithm and analysis are tight. However, the actual dependence on epsilon and P in our work is exponential. In fact, we conjecture that the same algorithm that we analyzed should obtain a 1 minus epsilon approximation by querying only a poly 1 over epsilon P degree subgraph. However, analysis is far from achieving such results. It's a nice open problem. So let me give you a quick introduction to the algorithm, which is a very simple Monte Carlo algorithm. So we have a parameter R, which controls the maximum degree of this subgraph Q that we query at the end. And what we do is we basically just take R independent realizations of G. These are part of the randomization of the algorithm. And then from each realization, we pick a maximum matching. And then our subgraph Q would be the union of these maximum matchings. In fact, this algorithm was known and analyzed before, but what we do in this work is we give an alternative analysis for this algorithm and show that it obtains all the way up to 1 minus epsilon approximation. So let me also mention a few words about the analysis. So we basically partition the edges of G into two subsets. We call them crucial and non-crucial edges. Naturally based on the probability that the edges appear in the optimum solution. The edges that have a high probability of appearing in the optimum solution are called crucial, and the rest of the edges are non-crucial. For instance, in this graph, the red edges would be crucial, and then the blue edges would be considered non-crucial. And then overall, the challenge of the analysis is to show that the crucial edges and the non-crucial edges can be used to augment each other and construct a large realized matching. And a key contribution of our work is to draw a new connection to distributed local algorithms. In particular, we design an algorithm which we call the vertex independent matching algorithm. And we show that if we run this algorithm on the set of realized crucial edges, and then commit the edges of this matching to the final solution, then we can actually find a large matching among the non-crucial edges that are not touched by the matching of the crucial edges. So to conclude, we show that the stochastic matching problem admits a 1 minus epsilon approximation by querying only a constant number of edges per vertex whenever epsilon and P are constant. And this dependence on epsilon and P is optimal. An important open problem is whether or not a 1 minus epsilon approximation can be achieved by querying poly 1 over epsilon P edges per vertex. Our conjecture is that it should be possible. Another interesting open problem is whether this two-third approximation barrier appears in various other settings for the matching problem, and whether a variant of this vertex independent matching algorithm can be used to beat it in those settings as well. Thanks.
Thank you, Sohail, for a great talk. If there are any questions, please raise your hands or post on the Q&A. While we wait for, oh, we do have a question already. So Hengu is asking, what is the approximation ratio if we take uniformly at random B matchings for some B that is like constant in epsilon and P? Of course, sampling B matching doesn't seem to be easy to do in polynomial time.
Well, I'm not sure what random algorithm you're exactly using to construct those.
Sorry, it's B dash matching, not B matchings.
I know. So I guess it depends on how the actual approximation factor depends on how what randomization you use. Typically, randomized algorithms do not find large matchings even if P is 1. So yeah, I'm not sure exactly what the precise approximation factor would be, but yeah, I don't think that the algorithm that I have in mind, a random B matching, would obtain a good approximation. So for instance, if every vertex picks, say, even root n number of edges uniformly at random, then you don't even get better than 0 approximation.
Yeah, actually, the first paper in this space, the Blum et al. Paper, highlighted some of these other algorithms and how they don't have guarantees that you would expect. Let me ask, there are 2 more questions. So Shushu Chawla is asking, you could also imagine taking multiple random realizations and taking the union of B matchings in those instead of just 1 matchings.
Right. Yeah, it's a little hard to actually think about what the approximation factor would be, but I'm happy to talk about this. But one thing is that it depends on the structure of the graph. Like, so if you have a clique, taking these B matchings would not be much different from taking actually multiple 1 matchings. But if the graph is like this example that I had here, you have to make sure that you pick those red edges in your subgraph somehow.
Shushi has a follow-up question asking what's known for adaptive algorithms.
Yeah, so in the early paper of Blum et al., they showed that if you allow adaptivity, so you can get 1 minus epsilon approximation within basically just the state of the art is you can get 1 minus epsilon approximation within 1 over epsilon p adaptive rounds, and in each round you pick only 1 matching. So yeah, so 1 minus epsilon approximation was known for adaptive algorithms. What we do is we show that adaptivity is actually not needed. You can just pick 1 non-adaptive subgraph and get 1 minus epsilon approximation.
Okay, thank you. Let's thank the speaker once again. This is the end of our session. A reminder that we have Slack channels under session 8C, paper 124. If you have any additional questions left, please feel free to use the Slack channels and the authors will answer your questions. Thank you so much for being here, and thank you to everybody who gave a talk today. Thanks. Mary, are you here still?
Oops, forgot I was. So I'm going to end the meeting for everybody.
Yeah, I was just like typing to find you. Thank you so much.
Yeah, it's like, oh.